6.4 and 6.5 are thermochemical equations and applying stoichiometry to heats of reactions, respectively. I put these two together because I think that it comes naturally to do stoichiometry right after we go over the thermochemical equations. When writing a thermochemical equation, you write the normal balanced equation, use your phase labels, they're very important here, and we also add delta H. As you've been seeing, our deltas have become squares, so when you see the squares, just keep in mind it's a delta if I haven't written anything else on there. So our delta H here is negative 891 kilojoules. It's very important to have that enthalpy term here, and that's what makes this a thermochemical equation. So you can interpret this by 1 mole of CH4 adding to 2 moles of O2, giving us 1 mole of CO2 and 2 moles of H2O, and that reaction gives off 891 kilojoules of heat. Again, like I said, it's very, very important to have the phase labels on here because the delta H depends on the phase of the substances. When you look in the back of your book at Appendix C, you should make note that a lot of substances have various phases: gas, liquid, solid, aqueous. So it is important that you look up the proper phase for each substance to get the proper delta H. The delta H term then it just becomes part of the equation. So if you're multiplying any equation by 2, if you're doubling the reaction, then you're also going to double the delta H. If you're dividing the reaction in half, then you would also divide the delta H. Any factor that you multiply the reaction by, you have to do the same thing to the delta H because it is now part of the balanced equation. If you flip the reaction and your products and reactants switch places, then you also have to reverse the sign of the delta H, because if a reaction generates heat one way, then the other way it's going to absorb heat. Here's a problem that I don't think is in your packet, but it's a simple stoichiometry problem. If you take a look, they're giving you the grams of CH4 in a balanced equation and asking you how much heat would be generated if we're combusting 10 grams of CH4. So the first thing we have to do, of course, is change grams to moles by using the molar mass of CH4. When we do that, our grams of CH4 cancel out. Then we know that the negative 890.3 kilojoules can be used in these types of problems too. And we know that that is generated for every 1 mole of CH4. So when we use that for our conversion factor, our moles of CH4 cancel out, and our answer is negative 556 kilojoules. Take a look at this next problem. This is for 6.5. 6.5 is just applying stoichiometry to the heats of reactions. So it includes kind of the problem we just did, and we're going to have a couple more problems using stoich. So if you look at this problem, it is on the next page, and how to solve it is on the next page. So this problem gives you the balanced equation, and it's telling you have 907 kilograms of ammonia and asking how much heat would be evolved. So this is the same as the last problem. We take the 907 kilograms of ammonia and we change it to grams first. When we do that, our kilograms, of course, cancel out. Then we use the molar mass of ammonia to change it to moles of ammonia. And lastly, we use the fact that negative 98.1 kilojoules of heat are evolved for every 2 moles of ammonia to cancel out our moles of ammonia. And we do the math. Our answer is negative 2.61 times 10 to the 6 kilojoules of heat. So believe it or not, this short little video just covered 6.4 and 6.5. Very short, very sweet. Hopefully you'll have no problem doing these types of problems. So have a great weekend, and on Monday morning we will be finishing up the problems for 6.4, 6.5. And we're also going to get our pre-lab for the enthalpy lab.